So the universal law of gravitation told us that the gravitational force acting between any 2-point particles is given by the following set of rules. The force is directed along the line that joins the two particles, it's attractive, and it has a magnitude that's given by the equation Fg equals big G times mass 1 times mass 2 over the distance between them squared. Well, what we want to do at this point is see how the universal law of gravitation and what it's telling us compares to how we've treated the gravitational force all semester long, and then see what that tells us about the gravitational acceleration. So until we introduce the universal law of gravitation, we've said that if you have some mass of m, sitting at or near the surface of the Earth, there's going to be a gravitational force that acts on m that pulls it straight downwards towards the surface of the Earth, and the magnitude of that force is going to be given by whatever your mass m is times g, the gravitational acceleration. The universal law of gravitation, however, says that we have another way that we can calculate out that gravitational force. Now we've got to be a little bit careful here, because the universal law of gravitation is really describing the gravitational interaction between 2-point masses. And clearly the Earth is not a point mass in this problem. But the way that it works out is that as long as we're outside the surface of the Earth, then we can act like all of the mass of the Earth is located at the Earth's center of mass. So what we're going to do is we're going to rearrange this expression. We're going to say, well, mass 1, we're going to let that be the mass of the Earth. Mass 2, we'll let that be the other mass that we have sitting up here at its surface. And so now the distance between those two particles, when we treat the Earth as a particle at its center of mass, is simply the average radius of the Earth. So what I can do then is I can change my notation and then set these two equations equal to each other, and that lets me solve for little g. Those two mass terms disappear. It doesn't matter what the mass is that I place up here at the surface of the Earth. I'm left with an expression that says the gravitational acceleration is equal to big G times the mass of the Earth divided by the average radius of the Earth squared. If I go plug in those values, so again, big G I know is 6.67 times 10 to the negative 11. The mass of the Earth is 5.97 times 10 to the 24th kilograms. The radius of the Earth on average is 6.37 times 10 to the 6 meters. So I plug in all of those values, and what I calculate out little g to be happens to be 9.8 meters per second squared. So the value of the magnitude of the gravitational acceleration that we've used all semester long really comes from thinking about how the gravitational force near the surface of the Earth is related to the gravitational force that we would calculate by using the universal law of gravitation. Now what this does is it gives us a way to calculate out the local gravitational acceleration at any point you want. So we can calculate out little g as the local gravitational acceleration that would act on any mass. That's given by big G times ms, where this s here is saying this is our source mass. This is the mass that's causing the acceleration. And then that's divided by r squared, where again r here is the distance between our source mass, the mass causing the acceleration, and the point where you have placed your mass m. So as an example, let's say I wanted to calculate out the local gravitational acceleration on the moon. The source mass here is clearly the mass of the moon. R, the distance between the center of mass of the moon and where I'm placing mass m, is just the average radius of the moon. So I plug those values in for my expression calculating the local gravitational acceleration, and I get the local gravitational acceleration on the surface of the moon is 1.6 meters per second squared. It's approximately 1/6 of the gravitational acceleration that we see here on Earth. Well, as an additional example, I could say, well, what if I want the local gravitational acceleration not on the surface of the Earth, but at some significant height above the surface of the Earth? And so part of what this lets you do is it lets you play around with, well, how does gravity change as you go higher and higher off the surface of the Earth? So when you compare gravitational acceleration at sea level versus, say, gravitational acceleration at the top of Mount Everest, how different are those? How different is the gravitational acceleration acting on some satellite that's sitting in low Earth orbit, let's say. And again, what you would do to calculate that out is get that the local gravitational acceleration at some height above the surface of the Earth, again, your source mass is back to being the mass of the Earth again, and r here is now the radius of the Earth plus your height above its surface. So the distance that's separating where you're choosing to put your mass m and the center of mass of the Earth is not just the radius of the Earth, but now it also includes this height h above the Earth's surface. What this equation for the local gravitational acceleration allows us to do is calculate out the gravitational acceleration at any point we're interested in. All we have to do is know what is the mass that's causing the gravitational acceleration there, and what's the distance between the center of mass of that mass and wherever you're going to place some other mass that ends up feeling this gravitational acceleration.